All right, good afternoon. It's really a pleasure to be here. Maybe I should have started by saying that an exponential function walks into a bar. That would be a nice continuation of the jokes that were presented last. Well, I'll skip it there, so I'll leave it there. Maybe come back to that joke in the end of the talk. But my talk is indeed related to exponential functions, but I'll get back to that as well. So it's really a pleasure to be here as part of the Danish representation at Q2B, and finally making it to the States this year. And as part of the Danish group, I'd like to advertise a little catalog that we have available in our booth down in the showroom. So if you're interested in learning more about what's going on in the Danish ecosystem, please come and see us there. Maybe grab one of those if they're still there. Otherwise, we're happy to explain to you what was in the catalogs before they were all sold out. Right, so I'm here to present to you some work of rather mathematical nature. It's a little dense. But on the other hand, I'll start by excusing or apologizing to the mathematicians in the room that my presentation of the topic will be light, because I'll try to skip over the most dense parts of this. Before I do that, let me just introduce to you the company that I represent. So I'm from Kvantify. We're a Danish startup company, about 3 years of age by now, 60 people. We work in software and algorithms for quantum computers, but we were born with a leg in both the classical side and the quantum side of algorithms. So we develop algorithms for classical computing, trying to accelerate things there, trying to make hard problems accessible, but also trying to see what can be done on the quantum side, trying to bring that to useful applications as soon as possible. We do have expertise across sort of the entire palette of problems. We have been working on both logistics and finance, but we are now recently starting to focus in more on life sciences. That's been a core part of the company from the very beginning, but we're sort of realized that this is where we can make the biggest impact as soon as possible, both on the quantum side and on the classical side. On the classical side, we're developing tools to assist the pharma sector at the early stages of drug discovery. In particular, we have tools out there for unbinding kinetics and for binding affinity calculations, things that were usually done through lab work in the pharmaceutical companies, tedious, costly work that we can now do in silico instead, and with really, really high precision. So if you're in the pharma sector, if that's of interest to you, please come and see me at the booth as well. So that's about Kvantify. So our approach is really to use the best of both worlds in all the things we're working with, and we believe that is the way forward. Quantum computers will not stand alone. They will always be backed up by classical computers. We demonstrated that approach earlier this year in a collaboration with a Danish biotech company, where we showed that we can actually use a combination of quantum computing and classical computing to do enzymatic simulations, and we can even go below sort of the chemical accuracy threshold in that combination of the technologies. I'm very happy to see that that works with current noisy quantum hardware. Right, so that's a bit about Kvantify. My reason for being here is actually that we take the opportunity to present some work that is rather different from the pharma tools that I just presented to you or talked about. This is some very computer sciencey and mathy work that my colleagues here, Alan and Casper, are responsible for. They're really the experts in the field. But we believe it's a rather interesting contribution they've made to the field, closing a gap by showing that there is indeed a provable exponential separation between algorithms, quantum-inspired algorithms, and real quantum algorithms for machine learning relevant problems. So this is what I'll try to make clear to you. How does this proof go about? What's it about? A bit of context for this work. So the HHL algorithm that's probably familiar to many of you spurred quite some interest in this field of machine learning by showing that there is an exponential speed up for solving linear systems. But then in the sort of the aftermath of that publication, or that work, it was shown that there's actually a lot of assumptions on how is the initial state going into the state preparation for running the HHL, how is that done? And it turned out that consumes a lot of computational power, which tends to eat up the speed up of the algorithm. So that was a bit of a sort of a tough thing to realize after the good things that came out of HHL. Then there's some work by Kiranidis and Prakash. After a few years later, they really tried to examine what was the problems or the challenges with the HHL, and so see, could they come up with another approach to this? and they worked on a problem that's called so building a preference matrix for recommendation systems. I'll get back to what a recommendation system is. And they tried to follow a sampling approach. They showed that it was actually possible to find another type of linear system problem where you could get an exponential speed up. So there's happy times again with this. Then some years later again came the work of Yu and Tang, showing that this problem that they found, Kioannidis and et al., where they had an exponential speed up, could actually be done as fast, or at least only with a polynomial sort of difference between the quantum-inspired algorithm and the quantum algorithm. So again, the happy days were gone, because this work by Tang really showed that all the previous examples of exponential speedups on ML-related algorithms could be reduced or could be done as well with quantum-inspired classical algorithms. So what remains is really to figure out, is this how it really is? Is there no way of finding an algorithm or use case where quantum computers can make a difference for machine learning? But I'll get back to that. That's really what the proof that was done by my colleague tries to fill this hole here. So the recommendation system problem, this is a little snippet from Amazon's webpage where they explain to the users of their services that they are recording the data, they're recording their recommendations of various products, and using that to predict what to recommend to other users. So it's basically this game here where you have a lot of products you want to sell. You have a lot of customers that buy your products, maybe recommend it. So one user may recommend the books, one may recommend the t-shirt, the shoes, whatever, or you may recommend several types of products. And then based on this knowledge, you want to know, will this customer here like that product? So you try to correlate what preferences that customer has with other customers and see, is it likely that if we recommend this product to that particular customer, that he or she will actually buy the product? So that's sort of the core of these recommendation systems. And in math, it's about constructing what's called the preference matrix, where you take all these recommendations in as binary numbers, zeros if you like the product, ones if you like them, zeros if you don't like them, and then you look for correlations between different segments of customers to figure out what is, good recommendations for particular customer groups. It's a very nice kind of system. There's a lot of efforts going into making those models efficient and predicting sort of buying customers with high probability. So a bit more mathy. This is a linear system that you want to solve. So you have some matrix M of a certain dimension. You multiply that by a vector, you get another vector out, and this is basically the problem that you want to solve. You want to find the inverse of that matrix to predict what are the good recommendations for your customers. One way of going about this is by sampling the matrix. So if you have query access to a matrix, you have an oracle representation of your preference matrix, you can query it, and then the game is all about, can I query this matrix as few times as possible and still get a value out that with high probability is close to the correct solution. So that's basically what you want to do when you're trying to solve these problems here. So this is also what my colleagues set out to do. They identified what are the best algorithms currently on the quantum side, what are the best ones on the quantum-inspired classical algorithm side, and how do they scale with different parameters that go into this problem. So on the quantum performance one, we have it scales polynomial with S, which is the sparsity of the preference matrix. So how many non-zero elements do you have in there? Then there's the kappa, which is the conditioning number for your matrix. It basically tells you how well can you approximate this matrix and still get a very, very reliable solution out. Then you have the precision, so this epsilon term, that it's an accuracy of how good an approximation or how good a solution is it, with how good accuracy is this the correct solution that you're getting out. And then finally, there's dependence on the size of the problem, so the log n term. Just looking at the quantum and the classical algorithms, they seem to scale exactly the same way. But the devil's in the detail. You see that the conditioning numbers are different. There's a little subscript f on the quantum-inspired one. If you look into how that kappa f is actually expressed, if you write it out, you'll see that there is room for an exponential separation between the classical one and the quantum one. So the dependence of kappa f on the problem opens up for an exponential separation in certain cases, then what remains to be done is to prove that there is no way that the quantum-inspired algorithm can sort of bridge that exponential gap. So that's what they set out to do, proving that there is no way you can come up with a classical algorithm that can match the performance of the best quantum one. And yeah, so in more bold terms, the result of this work is that there is a provable exponential separation between quantum and quantum-inspired classical algorithms for a problem relevant for machine learning, which is something related to solving linear equation systems. And in more mathematical details, you can see here below a little sort of snippet again from the paper where the core theorem of the work is spelled out, showing that with certain assumptions on the accuracy of the solution that you want, the size of the problem, all of this, you can actually show that there's a lower bound on how well the quantum-inspired algorithm can perform. All right. So like any other result of this kind, it works by reduction to a problem for which you know the bounds. So you need to figure out a way, how can I take my problem here, formulate it in terms of another problem that I know very well, and then I can establish the bounds of the algorithm that I care about. And the reduction, or the problem that's used for reduction here is that of welded binary graphs, the tree graphs. So they look pretty much like this figure here, that you have this big binary tree on one side that branches out into two new branches in every step of the tree, has a certain height, n, and then it's connected with another similar tree with some sort of circuit in between. And the way they're connected are essential here, because it was shown by Childs and collaborators previously that if you take just two binary trees, put them together, and then do a random walk on that graph, then it can actually be done efficiently in a classical way. You can get from the entrance to the exit in an efficient way with classical algorithms. But if you combine the two, if you weld them together in a different way, what they do is that you use a random algorithm to connect all the sort of highest level nodes of the trees on either side, so randomly picking one on one side, randomly going to another one, and then going back and forth, and then connecting the two graphs. Then you can actually make it really, really hard for the classical algorithms. The classical algorithm will make it very nicely up until the middle layer, and then it gets lost because it loses sense of what is forward and what's backward in this tree because of the randomness of that intermediate layer. So what is used in this result here is basically a mapping of the problem onto this particular type of graph. All right, so it's a graph. We call it G sub n with binary trees of height n. And then following the ideas of Childs, you also assign numbers, so strings of binary numbers of length 2n to each node in this tree, except the entrance. That one the entrance, that one you just give pure zeros. And then the game is that you set up an oracle that allows you to query this graph. So you start at the entrance, and then you move forward, and you query. So you just take a bit string, and you ask the oracle, is this a bit string that corresponds to a node in the graph? So remember, we assigned all these binary strings to each of the nodes. The oracle will either say, nope, I don't have such a node in my graph, or it will say, yes, it's there, and those here are the labels of the neighboring nodes in the graph. Okay, then based on that response from the oracle, you move forward in trying to make your way through from entrance to exit. And once you get a response from the oracle saying that you've just queried the binary string corresponding to the exit, then you've won the game. So that's exactly following the game that was set up by Childs and collaborators in their previous work. All right. So in a sub-result of Childs and collaborators, they show that there's also a lower bound for how the classical algorithms can work their way through this complex welded graph. And this result is showing that any classical algorithm that takes at most 2 to the power of n over 6 queries to the oracle finds the exit with probability at most 4 times 2 to the power of minus n over 6. Okay, so that's the result that's just derived as a sub-result in their paper, and this is really the result that's used in the work of my colleagues. Childs and collaborators, they go further, and they actually show that you can find a quantum algorithm that is exponentially faster in solving this random walk on the graph. Right, so the key steps of this proof is let's say we have a quantum-inspired algorithm for solving this linear system of the random walk. Okay, we assume we have this one. We associate A with that algorithm. When we assume that one gives us a good solution to the problem, then what we do is that we carefully match the matrix of the linear system, I mean the problem we're actually coming from. We try to write up a matrix that exactly matches the adjacency graph, matrix of this welded tree graph. Then what we do is we say, okay, we can simulate the algorithm alpha, the classical, the quantum-inspired one, and we can simulate by acquiring the oracle corresponding to the graph that we're now using to represent our linear system problem. And then turns out that the alpha will, the A algorithm, sorry, will with very high probability sample a good solution to this problem and find the exit. Okay. Now we have this assumption that we have a classical algorithm that's in there that works, and then we go back to the result of Childs and collaborators and use their result. First we show that using this adjacency matrix representation of the graph, we can show that the condition number, remember this kappa I showed before that tells you how well you can approximate the matrix? We can show that one is only polylogarithmic in the size of the matrix M. So that's an important step to realize that this one is only polylogarithmic, goes into fulfilling the theorem one I showed just before. Now the fourth step is what I was skipping forward to a little too fast. Now we use the result of Childs and collaborators to show that you can actually bound the number of queries needed to do this for the classical algorithm. And in this way, you can actually show that there is a lower bound using the result from Childs, etc., and using the reduction of the linear system problem to the graph problem, you can show that there is a lower bound on how efficient any quantum-inspired problem can be in solving this particular linear system. So that kind of fills in the gap that was there before, in showing that there could be good use cases for quantum computers to solve problems relevant for machine learning. Right, so what have I tried to convey to you? That it was unknown for a long time whether quantum computers could be of any use for machine learning. There were good suggestions for candidate problems and algorithms that were scaling in a good way. Then there was this problem that was shown that they could all be performed, or you could have a similar performance by any classical or quantum-inspired classical algorithm. It was bad. But now it has actually been shown that there are indeed problems, certain types of linear equation systems where you can find an exponential separation between the classical and the quantum algorithms. What remains to be shown is, of course, that there are lots of assumptions going into this linear system for which this can be shown, relating to the sparsity of the matrices, relating to the y-axis vector that you're solving for. So what remains to be done is to find, is there actually a practical problem where this solution applies to? If there is one such, we don't know what that problem would be, but if there's one, it would be super interesting to try to run that on a quantum machine. All right, I think that concludes what I wanted to say to you. Thank you very much.